The universe is a seemingly infinite expanse, stretching far beyond what we can observe or understand with current technology. It contains untold secrets, many of which continue to elude even our most brilliant scientists. These enigmas are not just curiosities. They actively hinder the progress of astrophysics, cosmology, and other scientific fields. New phenomena often contradict well-established theories, forcing experts to reevaluate long-held beliefs. The James Webb Space Telescope, JWST, humanity's most advanced observational instrument, has recently uncovered one such mystery that appears to challenge the foundations of modern cosmology. In particular, its latest findings suggest that approximately 900 trillion stars have inexplicably vanished, an event that could fundamentally reshape our understanding of the universe's origin, structure, and destiny. In this report, science journalist Joel Rohn delves into the extraordinary implications of this revelation. The James Webb Space Telescope, launched in December 2021 at a cost of approximately $10 billion, is widely regarded as one of the most ambitious space observatories ever constructed. Operated jointly by NASA, ESA, European Space Agency, and CSA, Canadian Space Agency, JWST has surpassed expectations within its first 2 years of operation. It was designed to observe the universe in infrared wavelengths, allowing it to peer through cosmic dust and observe objects previously obscured to visible light telescopes like Hubble. In July 2022, Webb began full-scale operations, capturing redshifted ultraviolet and visible light from galaxies billions of light-years away. This infrared focus enables JWST to look further back in time, closer to the moment of the universe's birth than any instrument before it. The telescope's sensitivity and precision have revealed star formation, galactic evolution, and planetary atmospheres with an unmatched level of detail, providing data that could answer long-standing questions in astrophysics or create entirely new ones. Of all the groundbreaking observations made by the James Webb Space Telescope, none have been as unsettling as the sudden and unexplained disappearance of roughly 900 trillion stars. Such a massive loss of celestial objects defies every known principle in astrophysics. Stars, even when they die, typically leave behind remnants such as white dwarfs, neutron stars, or black holes. Yet JWST data shows vast cosmic regions where stars that once glowed brightly are now completely absent, with no visible signs of their destruction or transformation. This phenomenon is not limited to a single galaxy but spans multiple galactic clusters, suggesting a widespread, systematic occurrence. Scientists are poring over reams of data, yet the mystery only deepens with each discovery. Some regions appear to have dimmed rapidly, while others seem to have blinked out entirely. The critical question remains unanswered. How could such an enormous number of stars vanish without producing supernovae, gravitational waves, or any other detectable signature? To explain this cosmic vanishing act, researchers have developed 2 primary hypotheses. The first suggests a less alarming scenario. The stars might not have disappeared at all but are now obscured by dense clouds of interstellar dust. These clouds could block their light from reaching telescopes, especially in visible and near-infrared wavelengths. Additionally, some stars may have reached the end of their life cycles and collapsed directly into black holes without undergoing the explosive supernova phase, a process known as direct collapse. However, this would still likely leave behind some detectable emissions or gravitational signatures. The second theory is far more troubling and speculative. It posits that we might be witnessing a phase transition in the universe itself. This theory suggests that regions of space are undergoing a fundamental change, possibly linked to quantum fluctuations or dark energy, resulting in parts of the universe literally ceasing to exist or shifting into a different state of reality, something completely beyond current human comprehension. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. The universe is expanding. He observed that galaxies were moving away from us, with their speed proportional to their distance, now known as Hubble's law. This revelation overturned the long-standing belief in a static universe. Importantly, this expansion doesn't imply galaxies are hurtling through space, but that the very fabric of spacetime itself is stretching, carrying galaxies with it. This concept is central to modern cosmology. Then, in 1998, 2 independent teams of astronomers, studying distant supernovae, made a startling observation. Not only is the universe expanding, but the rate of expansion is accelerating. This discovery introduced the concept of dark energy, a mysterious force counteracting gravity on cosmological scales. Today, the idea of a dynamically growing universe has become foundational in understanding cosmic evolution and future fate. The accelerating expansion of the universe has dramatic implications for our ability to observe and interact with distant galaxies. Although nothing can move faster than light through space, space itself can expand faster than light speed without violating relativity. As a result, galaxies that are currently visible to us are gradually being pushed beyond a cosmic horizon, a point beyond which their light will never reach us again. When we observe a star located 100 light-years away, we are seeing light that left it a century ago. However, with distant galaxies, especially those from the early universe, the light we see today was emitted billions of years ago, and the galaxies themselves are now far farther away due to ongoing expansion. The difference between look-back time and current distance becomes increasingly significant as we examine objects further away, making it clear that much of the universe is already beyond any hope of direct contact or travel. When observing cosmic distances, the stretching of space itself becomes a critical factor. As light travels across the universe, it is affected by the ongoing expansion, which stretches the light waves and alters their properties. This process results in what scientists call cosmological redshift. Essentially, the wavelength of light lengthens, shifting it from the blue or visible spectrum toward the red or infrared end. The farther away an object is, the longer its light has traveled, and the more its light has been redshifted. If the universe were static and unchanging, we would expect the light to remain at its original wavelength. However, the presence of redshift confirms that the universe is not only expanding but has been doing so for billions of years. Redshift is one of the key observations that supports the Big Bang theory and allows scientists to calculate the speed at which different galaxies are receding from us. The measurement of redshift in distant galaxies is a powerful tool that extends well beyond proving the universe is expanding. It allows astronomers to reconstruct the evolutionary timeline of the cosmos. By analyzing how much light from different galaxies has shifted, scientists can estimate their distances and ages. This, in turn, enables them to look back in time and study how galaxies formed, evolved, and interacted. When combined with brightness measurements and models of stellar life cycles, redshift data helps refine our estimates of the universe's age and rate of expansion. Moreover, it reveals patterns about galaxy clustering, the distribution of matter, and the influence of dark energy and dark matter over time. Redshift essentially functions as a cosmic fossil record, helping astronomers piece together a detailed narrative of the universe's 13.8 billion-year history, revealing not just where celestial objects are, but when they existed in cosmic time. The composition of the universe plays a direct role in how fast and in what manner it expands. Based on observations from missions like WMAP and Planck, scientists have determined that the cosmos is dominated by unseen components. Dark energy, a repulsive force that accelerates the expansion of space, comprises roughly 68% of the total energy density of the universe. This enigmatic form of energy appears to act uniformly across space and time, similar to the cosmological constant proposed by Einstein. About 27% of the universe is composed of dark matter, an invisible substance that does not emit or absorb light, but exerts gravitational influence and helps form cosmic structures. The matter we can see, stars, planets, gas, and dust, makes up just 4.9%. The rest is made up of elusive particles like neutrinos and photons, which are present but contribute minimally to mass. Despite decades of searching, no evidence has yet confirmed the existence of hypothesized exotic phenomena like cosmic strings or topological defects from the early universe. Armed with a deeper understanding of the universe's composition, scientists apply Einstein's theory of general relativity to model its long-term behavior. These models show that dark energy has become the dominant force in the universe, outweighing the attractive pull of gravity on large scales. Because of this dominance, galaxies not gravitationally tied to our own local group are being pushed away at ever-increasing velocities. The effect is not like a rocket speeding away, but rather space itself growing between us and those galaxies. Even with theoretical propulsion systems traveling at or near the speed of light, humanity will never be able to overtake this expansion. These galaxies will cross the so-called cosmic event horizon, a boundary beyond which light emitted now will never reach us. This leads to a deeply sobering conclusion. The majority of the universe is being permanently separated from us, and our cosmic neighborhood will only continue to shrink over time. There exists a profound and disturbing threshold in cosmology, the point beyond which space expands faster than light can traverse. This distance marks the edge of our observable universe, beyond which objects are effectively lost to us forever. Galaxies currently located around 18 billion light-years away might still be visible because of the light they emitted in the past. However, any light they emit now or in the future will never reach us, no matter how long we wait. This is due to the relentless acceleration of cosmic expansion, powered by dark energy. As a result, we are observing a frozen past of distant galaxies, while their present and future drift out of our grasp. The further we look, the more outdated the information becomes. Compounding the issue, the universe's matter and radiation are becoming increasingly diluted over time, reducing their influence on cosmic dynamics and allowing dark energy to drive even faster separation.